sorting the edge weights is the most time consuming step. Once you sort it, you can go through those iterations quickly. Okay? Here? Is easier, right? So you have to just pick the minimum edge weights and just keep including them and avoid a cycle. Now we are going to prove some theorems, properties. So, as I state there, you can have, say, two partitions of the vertices. One is, say, the set I, and the other is set J. So, given a graph, you can divide the vertices into two sets, I and J, like I showed before for the example. And which means if I put together the two sets, that's going to give you all the vertices in the graph. So I'm going to take a graph with V vertices and I'm going to divide those vertices into two sets, I and J, such that if I put together the vertices in the two sets, I get all the vertices in the graph. And a vertex is in only one of the two sets, which means no vertex is in both the sets. So if I take the intersection between the two sets, it's empty, which means no vertex is in both the sets. So we are going to have some edges that cross the two sets. Cross means between some vertex here and some vertex here, we're going to have some edges. Right? So these edges are called, or form what is called the cut set. Okay, so these edges form what is called as the cut set, and you can label that an IJ cut set because that's for these two sets I and J. So what the theorem states is, or the property is, if there is an edge, IJ, which is the minimum weight edge among all these edges in this cut set, then this IJ has to be part of a minimum spanning tree. Okay? So you have a graph with all edges and the corresponding weights, and you're breaking those graphs into two sets of vertices, I and J, and disjoint sets. And if you look at the edges that cross the two sets, and you have an edge, of course, among the edges there will be some way with a minimum weight. That edge, or with the minimum weight between crossing this cut set, has to be part of a minimum spanning tree. That's the theorem. Right? So we can look at an example graph that we had before, how we want to partition. Let's say partition this into something like this. Let's put these two, this is I, and let's put these three vertices as J. Alright? Here? So this is my I, connecting all those four things. These are the four vertices, I, and then this is my J. Now what are the edges that cross them? This, right? So the edges that cross the two sets are these. Right? Of weights what? 6, 15, 7, and 5. So the minimum weight edge is what? 5. And we know that 5 is actually be part of our minimum weight spanning tree. general, yeah, so now we have to get more general. So let's say this Hij, which is having a minimum weight, is not part of a minimum spanning tree. Alright? So if this Ij is not part of this minimum spanning tree, then you know some other edge has to be picked. Right? Because without, right now they are disconnected. So between among these four edges, whatever the number of edges, you have to pick one edge. Right? That connects to two sets. Otherwise, if you don't pick any edge that connects to two sets, they are going to be disconnected. Right? So between, in this example, between these four edges, we have to pick one edge that connects to two sets. The theorem states you have to pick the minimum weight edge that connects to two sets, but what we want to prove is by contradiction. So let's say Ij was not the edge that we picked to connect the two components, we pick something else. Let's say we pick I prime and J prime, this edge. Right? So let's say there was a minimum spanning tree, so we can denote minimum spanning tree as MST. So in a minimum spanning tree T, let's say I have this edge I prime J prime instead of Ij. Right? And we know from our, we know what? That Ij is a minimum edge weight, right? So the weight of Ij is going to be less than or equal to the weight of I prime J prime. Because this is a minimum edge weight, means at the best I prime J prime could also be, like in this case, 5 and 5. And this cannot be less than 5, it cannot be 4 or something, because we know this is a minimum edge weight. Right? So at the best that could be the same. So weight of H I comma J could be less than or equal to the weight of H I prime J prime. Clear? So, which means what? We have basically the components connected using this edge. So this is our tree essentially, isn't it? So this is our tree T, where these two sets are connected using I prime J prime. So what we can do is, instead of, since weight of Ij is less than or equal to weight of I prime J prime, we can include this edge and remove this edge and still connect the two sets. Right? Isn't it? Because these two sets were connected by connecting these two vertices with an edge. So we could remove that edge and connect the two sets with this edge. And still you'll have a tree because they are connected within this set and they are connected within this set. So we could remove this edge and add this edge. By doing that, are we going to increase the weight of the tree or not? This T tree, right, to start with, had this I prime J prime, and what we did is a transformation. What is the transformation? We removed I prime J prime and added what? Ij. So this is how we represent more formally. So you started with this tree T, you removed I prime J prime and added this edge Ij. And by doing this, what's going to happen to the weight of the new tree T prime? It's going to only decrease if possible. It's not going to increase. Why? Because if the previous tree, say, had weight 10, and we know this is going to be less than or equal to this, let's say some numbers, this is say 5 and this is say some 7 or 9 or whatever, right? So by removing this edge of weight 7 and then adding this edge of weight 5, we are going to only reduce the tree weight if possible. We are not going to increase it. So the weight of this T, the new tree T prime, is going to be only less than or equal to the weight of the tree that we started with. And our assumption is what? This is a minimum spanning tree to start with. Right? So this new tree T prime cannot be less than, strictly less than this, because if this is strictly less than this, it means what? this is not a minimum spanning tree at all, because a minimum spanning tree means something of the lowest possible weight. So we cannot find something less than this weight, right? So at the best this could be equal to, right? So this kind of contradicts the original assumption, because what it means here, you have some other edge and you can replace this with the minimum weight edge, and that's not going to increase, right? So which means instead of this I prime j prime, you could have as well as this ij, because by adding that edge instead of the other edge, you are not going to increase the tree weight. Is that clear? Because at the best you are going to only make it equal, you are not going to increase this, right? So it's going to be the weight of the new tree T prime is going to be less than or equal to the weight of the minimum spanning tree. So by doing this transformation, you are not going to increase the edge tree weight, you are going to only decrease it if possible. So which means instead of I prime j prime, you could as well have ij to be part of the minimum spanning tree. Okay? So that's the way you prove it. Is that clear? Okay? So always from now on start visualizing. You have two cuts like this, and then you have edges connecting the two cuts, and you typically pick the minimum edge weight crossing the two cuts. Okay? So now the second theorem. If there is an edge that is part of a minimum spanning tree, then its two end vertices are part of a cut set, and that edge is a minimum weight edge. This is what I said before, right? You pick any edge that was part of our minimum spanning tree. Same thing, this 5 was part of the minimum spanning tree, right? And these are the two end vertices, isn't it? C and E. So you try to form a cut set. It's your choice how you form the cut set. Let's say you pick these 4 vertices as part of one set and these as one set. Then again the same thing. This edge is the minimum weight edge connecting the two cuts. Okay? So the same thing looked at other way. So but here the thing is, you are given something as a minimum spanning tree, and you want to prove that this edge ij is the minimum weight edge in that set, in that cut, that crosses the cut set actually, that crosses the two cuts. So how do you prove this? Very similar proof. You pick something that is greater than 5. Okay? So what we want to prove, if an edge ij is part of a minimum spanning tree, then that ij is a minimum weight edge in that cut set. So let's say there is something else that is of lower weight. So again, so you have two cuts, and this ij is the minimum weight edge in that cut set. So we know that in this case, ij is part of the minimum spanning tree. So the minimum spanning tree has this ij. T has ij. And we want to prove that ij is a minimum weight edge crossing the cut set. So to prove that, let's say, assume a contradiction. There is now our I prime j prime is what? Is going to have a weight. So in this case, you are going to prove the other way. Assume this is going to be less than, strictly less than this. There is some other way edge I prime j prime that is of weight less than the weight of ij. So again the same kind of approach. If this is possible, then we could as well remove this from the minimum spanning tree and have this as part of our minimum spanning tree. Right? Because this will still connect all the vertices here and all the vertices here. So by doing this, since the weight of I prime j prime is strictly less than the weight of I comma j, you can further reduce the weight of the tree T, right? Because what we are doing is this transformation. So we are constructing a new tree T by removing I comma j and adding I prime j prime. By doing this, the weight of the new tree T prime is going to be less than the weight of T, because this I prime j prime is strictly less than the weight of ij. So by removing ij and adding I prime j prime, we are going to only reduce this. And this is not possible because this is a minimum spanning tree to start with. So if this is a minimum spanning tree to start with, it's a contradiction. So that's why there cannot be such an edge I prime j prime that is less than the weight of this edge ij. So this has to be the minimum weight edge crossing this cut set. So it's the same thing looked at different way. Okay? Is that clear? So I've given the statements also. So you don't need to memorize it. Just understand what I'm explaining. Then try writing your own words. Okay, so another theorem. So if an edge ij is not part of a minimum spanning tree, so there's now an edge ij in the original graph, and that edge was not selected to be part of a minimum spanning tree, then by including that edge in the tree, we are going to get a cycle. We know that any tree has a minimum number of edges to stay connected, right? So say this is the tree, and I am bringing in, so this tree spans. Spans means spread for all the vertices. So these are 7 vertices in your given graph. So if I add an edge connecting any 2 vertices, I'm going to get a cycle, right? And of course, you know all these edges have weights. So what the theorem states is, this edge that was not picked to be part of the minimum spanning tree, when you add that edge to this tree T, you are creating a cycle. And among the edges in the cycle, what are the edges in the cycle here? These are the 5 edges, right? This one, this. Among these 5 edges that are part of this cycle, this edge that was not included in the spanning tree is going to be the largest edge weight. Okay, so that's the theorem. So again, let me repeat it. You have a tree, minimum spanning tree. Minimum spanning tree means what? It spans, connects all the vertices, and the sum of all the edge weights is a minimum. That's a minimum spanning tree. And this tree was constructed from some graph. Like our example, you're given a graph and they're going through all the iterations and you get this tree. So there is some edge. Of course, there may be more than one edge also, right? But let's say there's one edge that was not part of this tree finally. So we are going to pick that edge and put it in this tree. So if you put any additional edge in the tree, you're going to get a cycle. And so what the theorem states is, this edge is having the largest weight among the edges that are part of this cycle. The other edges are these edges. Okay, so the others are tree edges. They are part of the spanning tree. This is the only edge that was not part of the spanning tree. So what we want to prove is, the weight of this edge is going to be the largest among the rest in the cycle. So based on what we have seen so far, how can we prove this? If you want to prove that this is the largest weight edge, let's say that this is not the largest weight edge, right? And there's something else that is part of this. right? There's some other edge that is part of the cycle that is of the larger weight edge, right? So that is the case, what we can do. So again, you know that the cycling means you already have a path connecting I and J through all these three edges, right? So I can partition the graph again to two sets, like these vertices, right? And I can, since this is not going to be the largest weight edge in the cycle, I can put it as part of the cycle and remove the edge that is having the largest weight. If this is not the largest weight, something else has to be largest weight, right? So I can remove that, and actually I have to form the cut set accordingly. Assuming that this is the largest weight edge, I can form the cut set like this and remove that edge that connects these two sets. So by removing this edge and retaining this edge, I'm going to have a tree, and since what I removed is going to be of larger weight than this one, because I removed the largest weight edge in this cycle, the weight of the tree is going to be further reduced. So again, we cannot reduce the weight of a minimum spanning tree further. Whatever is minimum, that's the minimum. So which means this edge that you remove cannot be of a weight larger than this one, right? So because if you want to retain this and remove this, it's going to reduce the weight of the tree, and you cannot do that. So again, that's how we can say that this edge that was not part of the tree is going to be the largest weight edge in that cycle. Okay? So we can look at that examples also. The graphs that we had. Let's pick up this. So this is a minimum spanning tree, right? So let's pick up something, say this edge DE. If I add that here of weight 15, that's going to create a cycle. What cycle? This is my cycle. And among these edges 5, 7, 7, 15, 15 is the largest weight, the one that we did not pick. So you can check any such edge. Pick up this edge. This is of weight 9. And what's the cycle here? The cycle involves just these three edges, right? So between 5, 7 and 9, 9 is the largest weight. If there is any such thing, even this 8, we put it here. 8 is the largest among 7, 5 and 8. So the edge that you did not pick, when you put it on the side, on the tree, is going to create a cycle, and that edge is going to be the largest weight edge. Okay? So that's an interesting property. Always try to have example like this and understand the theorem instead of just looking at it in abstract fashion. Because you have to write it in this fashion, but to understand it, you can go through this examples. That's why I'm going back and forth to the examples. Okay? So now what we want to prove is the correctness of this algorithm. Correctness means, so far we haven't proved that, right? So by picking the minimum edge weights, eventually we are finding the minimum spanning tree, right? So we want to prove that. We start with all the sorted edge weights, and each iteration you pick the minimum weight edge, and eventually you have the minimum spanning tree, right? So how do we prove that? So very similar to how we use for Dijkstra. So let's say the Kruskal's algorithm gives you the minimum spanning tree, but we want to prove that. So let's say there is some other minimum spanning tree that was not found using Kruskal's, but through some other means, and that spanning tree has a lower weight compared to what is determined by our Kruskal's algorithm. Okay? So let's say the Kruskal's algorithm gives us a spanning tree T, and we want to prove that this is a minimum spanning tree. To prove that, assume the contradiction that there exists some other tree T prime That's a minimum spanning tree, which means what? The weight of T prime is going to be less than the weight of T. This is what we are assuming. And we have to kind of argue that this is not possible. Okay? So let's say the Kruskal algorithm gives you some spanning tree T. You want to prove that's a minimum spanning tree. To prove that, let's assume the contradiction that there is some other tree T prime spanning tree that is of weight less than what is found by Kruskal's algorithm. And we want to argue whether such a tree T prime is possible. Okay? Now both are spanning trees on the given graph, which means both connect all the vertices. So let's say we have the vertices in the graph, something like this. So this is our tree T prime, and let's say this is a 6 vertex graph. So let's say this is our tree T. Both are spanning trees, both are connecting all the vertices, right? And for the weight of T prime to be less than the weight of T, basically are different weights, they have to have some difference in the structure. If both are the same, both have the same edges, then both should have the same weight, right? So if you want to argue that weight of T prime is less than the weight of T, both should have different structure. The structure means the edges, right? There should be at least one edge which is here, not here. Likewise, some edge here, not here. If both trees have the same edges, then the weights should be the same, right? So that's how you start discussing. So there should be some edge. What edge here is not there? So this, let's say there is an edge E prime here. That's not there.